Hello everyone, thanks for joining my session. My name is Baruffi. I am a solutions architect with AWS, and today we are going to be discussing about Karpenter. The name of my presentation is Just-in-Time Nodes for any EKS cluster auto-scaling with Karpenter. So let's just get started with a quick agenda. We're going to at a very high level discuss about EKS. What is EKS? Elastic Kubernetes Services on AWS. And we just want to set the tune and set the page, set the understanding of what is EKS, because Karpenter actually works on top of EKS. If you're not familiar with EKS, you might need a little bit of understanding of Kubernetes, but hopefully the quick overview will be able to provide the guidance. After that, we're going to talk about Kubernetes auto-scaling. What are the mechanisms that both on cloud native, Kubernetes native are available for us, but also what are the currently, implementation for cloud. After that, we're going to talk about some customer challenges based on those implementations, current implementations. And then we're going to talk about Karpenter and how Karpenter solves some of the challenges that we've heard from customers trying to do auto-scaling on Kubernetes. And in the end, we spend probably 10-15 minutes doing a demo, installing Karpenter, and actually showcasing how Karpenter can help you with a lot of flexibility and speed to scale up and scale down your clusters, your specific nodes within your clusters. So moving forward, let's do an overview of EKS. So EKS is short for Elastic Kubernetes Service. It's a managed service on AWS. EKS actually runs on vanilla upstream Kubernetes. It's also certified Kubernetes conformant for specific Kubernetes versions. At any given time, EKS currently supports 4 versions of your Kubernetes, which gives you as a customer time to test and roll out upgrades. Having a lifecycle management of upgrades on your Kubernetes clusters is really important, and AWS helps you with that. Because it's a managed service, EKS provides a experience for reliability, security, availability, and performance on top of EKS. On EKS, on the next slide, you see how you have data plane and control plane that can be managed for you on both sides. And the whole idea is by using EKS, you don't need to do a lot of the operations and what we call undifferentiated heavy lifting for managing your Kubernetes clusters. You can just rely on a managed service like EKS to take care of those tasks like upgrades, lifecycle management, security, and so forth. Of course, it's always a shared responsibility that some of the things will be taken care of by AWS, and some of the things it's your responsibility to proper configure, giving you the proper flexibility. So when we look at a high level overview of what EKS is, you have 2 boxes here. You have the first box that we're going to talk is the control plane. So when you look at the box on the right, which says AWS Cloud, it means that it's running behind the scenes by AWS. And here on the top, you can see that the control plane, which is a fully managed single tenant Kubernetes control plane per cluster. So once you create your EKS cluster, behind the scenes, AWS is going to create a single tenant only for you control plane, and you're only going to get the specific endpoint. You can create private or public endpoints. We call them cluster endpoints. And behind the scenes, if you're familiar with Kubernetes architecture, you have the etcd database, you have the API, you have the schedulers, and you have the controller. AWS is going to manage the control plane for you, and not only manage, but scale as needed. So you don't need to worry about that. It's all taken care on the control plane side by AWS. Then when you look at the left box, you see that the customer VPC, so that's the virtual private cloud that you have on your AWS account, and that's where you can deploy your data plane. So the data plane means that those are the nodes where your containers, your pods are going to be running on. You have kind of two types of node groups that you can create it. You can have a self-managed node group and a managed node group. With self-managed node group, you're actually responsible for all the configurations for your auto-scaling group, for managing AMI and everything else. With managed node groups, you have a managed experience for your data plane as well. So for doing upgrades, lifecycle management, scaling, those are actually going to be responsible to take those actions for you. Behind the scenes, you can actually also use Fargate. Fargate, it's a serverless container offering that does not require any specific node group, in the sense that you don't need any EC2, neither a self-managed node group or a managed node group. But with Fargate, that you pay per pod, and that is specific pod, that is specific running pod behind the scenes is running on the AWS account. So you can see here that the way it works, it creates an ENI within your VPC that links back to the Fargate micro VM that is running on the AWS cloud. Fargate also works on ECS, but has integration with EKS, like you can see here. For this talk, we're not going to focus on too much on EKS, data plane or control plane. We're going to talk about EKS auto-scaling and Kubernetes auto-scaling. So with that said, let's move to the next section. When we look at different, so what you as a customer or a user of Kubernetes, what are the available resources and configuration that you can fine tune for auto-scaling? So you're going to start at the application level. So you can separate auto-scaling and Kubernetes at two different categories. One is the application itself, and the other one is the nodes and the infrastructure. So the first two items are more focused on the applications that are running. The first one is called horizontal pod outscaling. HPA is the short version of that. The whole idea of HPA is you do a deployment on your cluster, and you decide how many replicas of that specific deployment you want to have. Let's say I want to have an Nginx server, and I want to have 3 replicas of that specific Nginx pod to be deployed across my specific environment. You can configure HPA on top of that deployment, and you can specify specific metrics, for example, CPU, memory, or even have your own custom metrics. And once you do that, HPA is going to look for that metric. And if a specific threshold that you have configured goes above, so let's say you configure that if at any given time the CPU aggregation of your deployment goes above 80%, you want to increase to another pod or another replica within your deployment. So HPA is going to take that job for you, and it's going to just add horizontally more pods for as much as you have configured and for whatever metric you have configured. So that's what is called HPA. But you also have another option, which is called the vertical pod outscaling, which is short for, VPA is short for. VPA is less common in a sense, because Kubernetes is really good at distributed systems horizontally, but you also have an ability to actually change a pod that is running, for example, with 2 gigabytes of memory, but if a specific threshold has been achieved, you want to create a new pod with 4 gigabytes of memory. So the same things that works on HPA now, instead of adding new replicas on your deployment, is just going to recreate a new pod with more memory available for that specific pod. But those are always looking at your application. Those two configurations, both HPA and VPA, don't actually look at the cluster itself or add more infrastructure node. You only do at the application level. So you actually need to, if you want to run a flexible and elastic Kubernetes cluster, you also need something that is responsible for creating more nodes for you. With that said, that's where cluster autoscaler comes in. So with cluster autoscaling, if let's say you have 2 nodes on your data plane and you try to schedule, in this example, 4 more pods, but there are no resources available within those existing 2 nodes on your node group, A cluster autoscaler, once you install and you configure and integrate it with your provider, let's say in this case AWS, cluster autoscaler will look for panning pods, and we say, wow, I don't really have resources currently available for me to deploy those 4 panning pods. So the cluster autoscaler will go and will talk to the autoscaling group as part of your node group, either a self-managed node group or a managed node group. So the cluster autoscaler itself will go and will talk to the API of your autoscaling group, and you say, please spin up a new node, so a new EC2 for me within that specific autoscaling group. So then I can, go and book and go and actually schedule and run all my 4 pods that we're panning. So behind the scenes, each autoscaling group will increment the size based on the recommendation of the panning pods. This works fine for most applications and workload. However, as Kubernetes and EKS have gained broader adoption, customers are moving for a variety of different workloads. And as you can see in this example, it's actually just creating a new instance of the same instance type within the same autoscaling group. And that's where some challenges come into the picture. So what we've heard some customers bringing some feedback and saying why potentially cluster autoscaler doesn't work every single time, or there is potentially improvements that should be made. So nearly half of AWS Kubernetes customers have told AWS that configure cluster autoscaler is challenging. And we are gonna now just go through some of those challenges to set a scene on why it was important for us to create Karpenter. So first of all, node groups and autoscaling group sprawl. Different workloads will need different compute resources. So a AI ML workload, we have a very different requirement than, for example, your web application or your batch application, right? Unfortunately, with cluster autoscaler, the only thing that the cluster autoscaler is able to do is to add new instances of the same type on your existing managed node group. You can create multiple managed node groups with different instance types, but that adds a lot of complexity, in managing those, right? So what customers have told you that not all workloads needs to be isolated on specific node groups, and balancing the needs of specific workloads adds a lot of complexity, because now you need to manage multiple autoscaling groups and multiple managed node groups, and it becomes just cumbersome, and it's really hard to achieve proper performance for cost and also for availability. As an example, if you need Spot, you can't mix and match, in a specific managed node group is Spot and on demand. You need to have multiple managed node groups that behind the scenes, each one of them have an autoscaling group, and it becomes really challenging how you actually provide availability for Spot interruption, or best practice for example, is spreading workloads across the Z while always thinking about cost and trying to improve cost and performance for those workloads. Another challenge that we've heard from customers is cluster autoscaler actually sometimes can be very slow to respond for capacity needs and spike workloads. So if you think about it, ETL jobs or GPU training jobs or ML workloads, the speed that it's required for those workloads like big data and ML workloads to be spun up is critical. Delay in providing those capacities for these workloads can slow down innovation and potentially decrease the satisfaction of your data scientists and engineers. This job typically spin up several nodes of expensive accelerated EC2 instances, for example, GPU, very expensive GPUs. So you want those to be very quickly spun up, but also very quickly spun down. And a slow scale down means waste resources, which you don't want to be in the business of. Another challenge, it is very hard to balance utilization, availability, and cost. So typically with cluster autoscaler, it's hard to get high cluster utilization and efficiency operation while not over provisioning resources to ensure a consistent user experience. So what this can result is in a low utilization and lead to waste resources that impact, which the impact can be significant. So as an example, let's say you want to make sure your application is running across multiple availability zones now, but have a different resource requirement, then you potentially need to have multiple auto-scaling groups, and that adds just a lot of challenge managing those auto-scaling groups that are across AZ, and you want to make sure that they are fully utilized. Becomes very challenging and sometimes potentially impossible to not have wasted resources. So with all those three challenges we've so far have discussed, we have come up with Karpenter. But what is actually Karpenter? So Karpenter, it's a open source, a flexible and high performance Kubernetes cluster autoscaler. So instead of actually deploying cluster autoscaler, you can actually deploy Karpenter on your EKS. It is open source and Kubernetes native. It doesn't have any concept of group, so it's what we call a groupless approach, and we're gonna talk about in a moment why it's called groupless. But it's pretty much automatic node sizing. So instead of having a specific requirement of, or a specific, I guess, blocker of just being able to launch instance of the same type that you have on your auto-scaling group, with Karpenter, it can look at the specific requirements for the pending jobs and choose the best performance and cost for that specific need at any given time. And it's also much more performant at scale because it has some changes on the way it behaves compared to cluster autoscaler. The way APIs and the way it's actually looking for pending pods on your cluster is a little bit different. The goal is to launch 1,000 pods within 30 seconds. That's the goal that Karpenter has set in mind, and it can, depending on your environment, actually achieve that. So let's look at how Karpenter works. Very similar to cluster autoscaler, when you have pending pods, Karpenter will always going to look at the schedule on Kubernetes, because it works integrated into Kubernetes native ecosystem. You look for pending pods, and those pending pods, looks at existing capacity in this case and see, well, I can't actually deploy more pods because it's full here. So pending pods becomes an unschedulable pods, and then that's where Karpenter comes in. So this would actually replace your cluster autoscaler. You're not gonna have, in this case, cluster autoscaler here. You have Karpenter deploy, and Karpenter, we actually go and instead of talking to an autoscaling group, because there is no groups, we'll go and we'll talk to the EC2 Fleet API. And the EC2 Fleet API provides a bunch of benefits. And behind the scenes, what Karpenter does, it looks at the specific requirements for those unschedulable pods and will find just-in-time capacity that is perfect for what you need. So you can configure, and it's very flexible what type of configuration allows you to do. But if you don't provide any specific limitations of the instances that you can choose, you'll find the specific instance that can fit your requirement, while also improving for cost and performance. And you make that decision for you. So it's also deeply integrated with Kubernetes. So you look for watch APIs, you have a lot of labels and finalizers. And like I said, it does a lot of the automated instance selection. So you match a specific workload to a specific instance type. Karpenter also works really, really well with Spot. So if you configure a specific provision, and we're gonna talk in a moment what is a provision, but if your provisioner has support for Spot, and you can mix and match Spot and on demand, you can have both, being supported. It can actually look for what cheapest and most performant Spot is available on this currently a specific availability zone that you want to deploy, and actually pick and choose that and deploy those for you. And it can also hand interruption for you. You actually has integration with the 2-minute interruption system that Spot has in place to allow your applications to potentially be rescheduled before the node interruption is in place. Another really good thing that Karpenter has actually done is the ability to consolidate. And consolidation is a feature that actually looks for opportunity to improve your cluster utilization over time. So Karpenter does not also works on scaling up and down, but also look at your cluster high level and look at which current nodes you have in place, and if there is potentially an opportunity to maybe remove some of those nodes and bring up other nodes that are more performance and a price optimized for you. So you can reschedule running pods onto existing clusters that are underutilized at the cluster capacity, but you can also launch new, more cost efficiency nodes within the cluster and replace potentially nodes that were much more expensive. So let's say you have, in this case here, you have 3 nodes that are potentially, M5 large. Let's just give an example. Karpenter will look at that and say, well, I can potentially spin up an M5 2x large and maybe then an M5 medium, and actually bring all those capacity to those 2 instances that are going to be more performance and better for your price. So that consolidation is a feature that you can enable. If you don't want the feature, it's okay, because it's actually going to reschedule the pods, and you want to make sure your application is highly distributed within your cluster, so consolidation doesn't ever bring your application down, but that actually optimizes capacity quite a lot. So when we look at how Karpenter works, right? How Karpenter provisions a node on AWS. So let's first look at how Cluster Autoscaler does. So Cluster Autoscaler, we look at, let's say you have an application scheduler or HPA is triggering a specific pod to be created. It gets into a pending pod scenario. Then the Cluster Autoscaler will actually look at those pending pods. We'll talk to autoscaling group, and then autoscaling group will talk to EC2 API to increase or decrease, whatever, in this case, increase because you have pending pods, increase the number of nodes that you have on your node group. Now, the way Karpenter works is instead of having to talk to cluster autoscaler and the specific autoscaling group, pending pods will actually talk directly. A Karpenter will watch for those pending pods. Those pending pods will then actually set an action on Karpenter. And instead of Karpenter talking to EC2 API, Karpenter talks to EC2 Fleet instance, which is much more performance when you're trying to grab, what is the capability and possibilities that Karpenter can deploy on a specific availability zone in a region. EC2 Fleet is the one responsible on the AWS side to make those decisions. And consolidation, instance orchestration responsibility within a single system, it's what Karpenter does. And we've talked about groupless provisioning. So what actually Karpenter does, it's an application first approach, because it's always looking for the pending pods and grouping those pending pods, which is called bean packing. So every time there are pending pods, you're actually going to bean pack all those pending pods and look at what is the simplest node provisioning that will make sense for your cluster. And the way you configure Karpenter, you'll see on the demo, it's really simple. You just have 2 objects. One is the provisioner, and the other one is the node template for your specific provider, in this case AWS. And it reduces a lot of the cloud provider API load, because now it's going directly to the EC2 Fleet API. It doesn't have the limitations that how many times you can call autoscaling groups, which the cluster autoscaler had. And it reduces the latency significantly. So you choose the instance type from the pod resource request. So you always, when you have when you're doing deployments, you always want to make sure you set the requests of memory and CPU, and that's what Karpenter we actually use, to look at how much memory and CPU it requires. Then you choose the specific node as per pod scheduling constraints. So if you have constraints of specific availability zones that you want that pod to be deployed, or potentially some specific, instance types or GPUs, it's gonna look at the pod deployment, specific like labels, and then Karpenter read that and make a decision based on those constraints. And that capacity is directly done on EC2 instance fleet, and then you track the nodes using native Kubernetes labels. And you also bind it. So this is a specific one. It binds the pod early to the node because it doesn't need to wait for the cluster the cluster autoscaler to make any decision like it was before. While it's actually creating the node behind the scenes, the kube scheduler is already kind of downloading everything that it needs to do, and it becomes ready. The schedule for the node becomes ready. It can start preparing the node immediately. It doesn't need to wait much how the cluster autoscaler needs, including the pre-pooling of the image, and this can actually shave seconds off node per node startup latency. So it just says a very nice feature that helps Karpenter be more reliable and fast when actually doing those scaling activities. So let's just quickly look at how Karpenter can scale up. Let's see, we have a specific panning pods here on the top. Karpenter will look at those panning pods and will create a new node, right? And assuming it has, you have targets here because you have requests set on your application, so it knows how much at both at the node level, but also at the cluster level, what is the utilization and the target that you want to set for a specific one. In this case, you can set up provisioners. By default, it has all instances types able on that are included that Karpenter can pick and choose, but you can specify, and we have some examples that I'm going to show of specific instance types that you want to make available. And then when we have scaling, we have different options. So we have both, we talked about consolidation, and we're going to show an example before, but you have two options. You can either use the TTL seconds after empty, or you can use the consolidation. They are, mutual exclusive. Consolidation is more like a newer feature, but before consolidation existed, you have this setting set TTL seconds after empty. In this case, in this example I'm showing you, is set as 10 seconds. So what this feature will do, it will look for nodes that are empty. In this case, I just removed some pods from my node, and 10 seconds after this, if the node is still empty, you're actually just going to remove the node completely. And one thing that I just want to mention is it doesn't actually care about the daemon sets, because daemon sets are looking at every single node. You just look for pods. So it is smart enough to realize, if there are 3 daemon sets running at that cluster, at that node, it doesn't really cares about that because it knows the daemon sets actually running across all nodes. So remove that. I talked about Beanpack. The cool thing is it combines all those specific panning pods requirements and has well-known labels that you can define on your specific deployment that are actually configured at the node as well. So let's say you want to run this specific application on ARM Graviton 2 processor, you can actually define those specific labels, and when Karpenter is doing the Beanpacking, is going to make a consolidation decision on how they can organize all the panning pods you have on the queue. And then consolidation, which I recommend rather than using, there are potentially reasons why you want to use TTL seconds after expire, but potentially consolidation is a much more broader and feature-rich solution that allows you, if you enable here on your provision, as you see, consolidation enable true. Let's say in this example, you had 5 pods within this node here on the right. What you can actually do, once it goes back to 2, you can see that you have a lot of underutilized resource. Karpenter will look at that if you have the consolidation enabled, and you say, you know what? I can actually run those 2 pods in a much cheaper node. So it's gonna spin up the node for you. It's gonna move those, it's gonna spin up the node for you. Then it's gonna move those pods into the new node, and finally it's gonna remove the old node. So in that environment, it actually allows you to, delete a node when pods can run free on capacity that exists in the cluster. But it can also delete a node when you have a specific, you don't have a lot of requirement for that big node that you have, and you can just create smaller ones like the one you saw here. That is just, a replacing of a node. In this case, a specific, so continue the example here. You had 4 pods on this one in the third node from the top. Now you only have 1 pod. What it's actually going to do is going to remove from here. It's going to move from the one at the bottom, and it's just going to remove. So it keeps an idea of cost optimization, which is really important to scale your Kubernetes solutions. So here is we are just going to spend a few examples here how you can configure your provisioner. So your provisioner is the Kubernetes object that once you deploy Karpenter, and you see on the demo, you can provide specific configuration how your provisioner can behave, and you can create multiple provisioners with different weights, or you want to match your specific pod to a specific provisioner. There are actually labels that you can actually mix and match. So one example for the flexibility of provisioner is the ability to select purchase options. So you can select capacity type. In this case, you have, requirements, capacity type. You actually are choosing a spot and on-demand. When you have a spot and on-demand configured at the same time on a specific provisioner, Karpenter will always favor a spot, and it's only gonna pick on demand if there are spot constraints. So if potentially the good options for a spot to launch a new EC2 instance for you are not available at that time, then it's gonna default back to on demand. But you can also select different architecture types. You can have provisioners that can deploy both ARM 64 Graviton2 processors and AMD 64 processors type with x86. So that means that that will look for the specific architecture type that your panning pod needs, and if it needs an ARM, and there is no capacity available in your cluster, is actually just going to go and deploy a new ARM Graviton2 EC2 node. But you can also do that for AMD 64. Another capability is you can restrict instance selection by diversification across different configurations. So you can define the size, the family, the generation, and the CPUs. So in this example, you don't want Karpenter to spin up instances that are nano, tiny, small, and large. You only want medium, X large, 2X large, 4X large. So you can create this specific requirement on your provisioner, and then Karpenter will always look at those. And if you can have multiple provisions, but if for whatever specific configuration have a panning pod that has gone to that specific provisioner, then you just use the configuration you have in place. But you can also have availability zone. You can say, well, this provisioner should only deploy new nodes into US West 2A and US 2B availability zones. So you can restrict for availability zones if you have a requirement that you want to make sure your applications are only run, or a set of your applications can run on this environment. Another thing you can actually do, this is just a new specific provisioner. You can create different provisioners. In this case, is not the default provisioner. It's called West Zones. And you can say, well, West Zones can only deploy within these 3 availability zones on US West 2 region, and you can do either spot and on-demand. So this is a very simple provisioner. You just pick whatever instance type is the more performant and available at the time. It's very likely it's going to be a spot instance if it's available for you. And you can also isolate expensive hardware. So if you have needs, for example, for applications that need a GPU, you can specify which instances you want that this specific provision to deploy. So in this case, GPU, you just want P3x8x large or P316x large. But then what you do is you create a tent on those nodes. And if you're familiar with tent and toleration, it means that only pods that have a toleration to support this specific tent will actually gonna go and be able to request and provision those resources within these nodes. So if you don't specify on your pods or deployments a toleration to support this tent, this is not gonna be selected. But that gives you an ability to have different provisioners to fit your specific use case. And this is all declarative using Kubernetes custom resources definitions using CRDs. So hopefully I provided a little bit of information on Karpenter before we do the demo, but there are some takeaways that if you're looking to implement Karpenter, you should be familiar with and or at least evaluate. The first one is if your application can support disruptions, in the sense if you have distributed your applications across multiple nodes and availability zones, please use EC2 Spot instances to optimize for cost, because Karpenter actually looks for those node interruptions for a spot and reschedule automatically your pods into a new instance that will configure. But of course, you don't want to be in that business. If you only have one pod, for whatever reason, you have a stateful application that can only run in one pod, you probably want to avoid a spot. So it needs to be a case by case, but if most of the times, if you're using stateless applications on Kubernetes, you should be using pod. And then you can use you're going to use provisioners to ensure that your scaling nodes and spots are actually implemented with best practice by default. Like I said, you can have multiple provisioners, but you can also have, you should have a default provisioner with a very diverse instance type and availability zone. So if you don't have specific needs like GPU in that example, you can just let Karpenter choose what is the best for you, given a wide variety that you have configured on default provisioner. But then you configure additional provisions for different compute constraints, like you have a GPU or you have, jobs that you want to make sure it runs on a specific instance types because of performance or architecture. Then you create those additional provisioners and you link your deployments to those additional provisioners. And of course, you want to control your scheduling using Kubernetes native solutions like node selector, topology spread constraints, taints, tolerations, and provisioners. You actually integrate that within your scheduling of your application. And of course, you should use horizontal pod outscaler in conjunction with Karpenter. So you have HPA focusing on the application scaling, and you have Karpenter focusing on the cluster scaling, spinning up instances as needed for specific requirements. And then before we go into the demo, please look at these resources. I'm just gonna go quick through them. The first one, you have Karpenter web page, Karpenter.sh. You have all the documentation and everything available there. You have a lot of examples and you go into a lot of details on how Karpenter works. Because Karpenter is open source, you can just look at the Karpenter specific GitHub. If you have an issue, feel free to just create an issue on GitHub, or if you need some help, the community is always there for helping. You have a workshop if you want to play around on your own with Karpenter. You have 2 workshops here. The first one, the Karpenter workshops with the ec2spotworkshop.com. It goes in depth on Karpenter, so it's a really good workshop. And if you just want a more high level, you can do the EKS workshop and go to the Karpenter selection and play around with those. And there is a really good 50-minute video if you just want to hear from other SMEs on AWS talking about Karpenter. You can just click on that button. And before I go on the demo, the only thing I want to mention is Karpenter currently only supports AWS as a provider, but because Karpenter is open source, we do expect in the future that potentially other providers can adopt Karpenter and also make available for their users to utilize this flexible way of auto-scaling on Kubernetes. So we'll see you in a moment on the demo. Okay, so let's jump into the demo. So I have created before a EKS cluster. So if you just wanna go and take a look at the nodes that I have on my cluster. So I have actually 2 nodes already created. Those are actually nodes that are managed by a managed node group on EKS. Those are not managed by Karpenter. I just wanna, start from a clean slate. So you need a place where Karpenter will work. So you can actually have Karpenter being deployed on a managed node group, but that managed node group doesn't need to scale or anything like that. So if I go on the console and I just show you, I have one managed node group, which 2 desired instance, which are the ones I showed, and they are, up and running. And if you look at the pods that I currently have available on this node here, nothing fancy. I just have this KubeOps view, which is a application that I can look at the stats and a nice visualization of my nodes. AWS nodes, each of the specific nodes to talk to AWS, Core DNS, Kube Proxy, and Metric Server. If I want to use HPA, I need Metric Server, so it's deployed. Behind here, it's a nice tool. It's called EKS Node Viewer. It's open source. You can just Google EKS-Node Viewer. This actually shows in real time what is the currently state of my EKS cluster. So the one on the top here is the cluster aggregation. You can see the price per hour and the price per month. And below here, it's per node. Which instance type, how many pods are running each of them, instance type, the price, if they're on demand, if they're ready. You see as I go through and install Karpenter, and once Karpenter will actually go and deploy things for me, you see that this will keep changing. So that's why I'm sharing with you. So I have everything already set up. I just want to install Karpenter. And so Karpenter is available as a Helm chart. I have this command here that I'm just going to deploy. What is this actually doing? It's creating the Karpenter installation for me. I have already some environmental variables and some pre-configuration that I've done. If you want to deploy Karpenter with integration with EC2 Spot, there are a few pre-configuration you gotta do, like creating a SQS queue, making sure you're creating rules for that SQS queue from Event Bridge and so forth. Those were already created for me. So I have deployed Karpenter, and now if I go and I look, so let's look at the pods that Karpenter have. So Karpenter is deployed within a specific namespace called Karpenter. So if I look at the pods that Karpenter has actually deployed, I can see that I have 2. So Karpenter doesn't work as a daemon set. Karpenter is just a deployment. And if you look here, kubectl get deployment on the Karpenter namespace, you're actually going to see that it's just a deployment. And Karpenter works in an active standby approach. So there are 2 pods and they are going to be running across different nodes, but only one pod at a given time is responsible for making those decisions and making the scaling actions for me. So the other one will actually take place as the lead if something happens with the first one. So it's important to understand that it's a high availability scenario. It's not using daemon set, it's just a deployment. They have both enabled. So what we're gonna do now, we have created Karpenter, but I haven't created my provisioner. And provisioner is what actually is responsible for making those decisions. You saw on the slide before, is how you tell which decisions you want to make when there is a specific scaling activity. And then there is also the AWS node template object that is responsible to telling Karpenter how he actually goes and talks to the cloud to scale up and scale down applications on EC2 instances on your AWS account. So I have pre-configured a very simple example here. Just gonna paste it and I'm gonna show it to you. So what I've done so far, I installed Karpenter and I have deployed a provisioner and I have deployed an AWS template. So let's just quick look at the provisioner and see what this provisioner tells us. So if I go kubectl get provisioner default -oyamo, that is the name of my provisioner. So what this provisioner is telling me that every single this provisioner has a label of intent apps, and we'll see in a moment why that is important. You can also create some limits on your provisioner. So the provisioner will keep a count of how much CPU and memory it has controlling, and you can define how much memory you want to give memory and CPU aggregated on all the instances that provisioner will create. What is the limit? So this provisioner will never go above 1000 CPU and a terabyte of memory. Then I provide a specific name for my provisioner. This is the default provisioner. And here I provide some requirements. So I'm saying that for my capacity type, I just want to do spot. So this is only going to do spot. And then I'm saying for my instance types, I don't want to be nano, micro, small, medium, large. I only want instance to actually be 2x large and above. And then for operating systems, I only want Karpenter to actually deploy Linux. And for my architecture, I only want Karpenter to actually deploy AMD 64 instances. And the instance category are only C, M, and R. I know there is a lot here. You don't need to do that. If you just leave all empty on the requirements, Karpenter will figure out by itself. But in just showcasing how flexible and customizable a provisioner can be. And I'm saying that instant generation can only be greater than 2. So, you won't be able to deploy like an M2. I don't even know if those are still available, but you won't be able to deploy an M2 instance if that was available. And then I'm not using consolidation in this specific example. I'm just using the TTL seconds after empty. So 30 seconds after the node is empty, it's going to remove. And then this is an interesting one that it says TTL seconds until expire. You can create expiration dates on your nodes, which helps you with lifecycle managements. And if you want to do new AMI updates, this is a good selection. You can specify a specific number here. And after that number has expired, Karpenter will automatically create a new instance with the new AMI if you have a new AMI in place, or you use the old AMI if you don't, and then we'll start deploying those pods from this old instance to the new instance. So you always keep those instances fresh. The other object that has deployed is called the AWS node template. And if we go just to show YAML here, you can see that what this does, it is responsible for, so this is the important piece here. So what this does, this is responsible for telling a Karpenter, how do you actually deploy new instances? Like which security group do you use when you're deploying those instances? Which is the subnet that you use when you deploy these new instances? And potentially, you want to select some tags on those instances as well, right? So you can, provide this here. There are many more other configurations. You can specify an AMI, a specific AMI here. You can do much more configurations, and you can check that out on the Karpenter documentation. But let's go and try to do a deployment where Karpenter can go and spin up new instances for me. So let's just go here, and let's just create a specific deployment using inflate. So I have deployed, so here I'm deploying this object called deployment, 0 replicas right now. And I'm telling here on this deployment that I want to select nodes with intent apps. And if you remember, Karpenter, once the nodes are created, will have intent apps. So I'm just telling this just to say, please don't deploy this application on the existing 2 nodes. Deploy with nodes that have this label, intent apps. And then Karpenter will actually spin up those nodes with this label. And just doing a pause container, and I'm giving 1 CPU for each pod and 1.5 gigabytes per each pod when I deploy. But because, of course, if we do kubectl get deployment, I have 0 replicas, so it haven't created anything for me, right? So let's just see 1 second, deployment. So you see here that I have inflate. It hasn't deployed, it hasn't done anything. So what I want to do here, let's just go and actually scale this up for us. So let's just create 1 replica to start with. So let's just go create 1 replica. So you see now in a moment down below, keep an eye down below, you see, there you go. Karpenter looked that there was spanning pods because there wasn't any node that that was able to sustain all the requirements that those pods had. So now it's creating an R4X large that is its pod, because remember, my provisioner only said this pod, it was not supporting on demand. It tells me the price, and it's an L4X large. So you can see now that it's actually spinning up the node. It'll take maybe a minute or so to spin up the node. Once the node is up and running, you see, and we can keep an eye. Actually, let's look at the logs. So we can look at the logs for, let's just do one thing here. Let's look at the logs for Karpenter. Let's look at the logs for Karpenter and see, you know, what the logs are telling us. So if you do kubectl logs -n Karpenter, if you see here, let's just wait a moment. You can see, yeah, so you can see that it started, let's see where it actually says. Oh, sorry, this is actually not, so remember how I said that Karpenter has 2 pods. I select the pod that is not the lead, is the standby one. So let's just select this one. Second, let's just select this one. There you go, kubectl logs -n Karpenter, and let's look at the logs. So you can see that found provisionable pods, found provisionable pods, compute new nodes to fit pods. So he found the pending pod, then he launched a new node here, and then, you know, he discovered the security group for my node, he discovered the specific Kubernetes version, discovered the AMI, create a launch template, and launch the instance, which is this instance that you see here. And if we now look at the kubectl get nodes, you see that I have a new node, which is the one down below here that ends with 145, that has 1 pod. So if you see here, kubectl get pods -o wide, and we see that this pod for inflate is running on the 145 instance. But what happens if I want to scale this specific, let's say I want to scale this deployment a little bit more. Let's say I want to scale this deployment to have 10 replicas. What will actually happen? So if I go and I do a deployment, okay, I need 10 replicas, right? So you see that it has scheduled 5 pods here. And now he said, well, 10 replicas won't fit in this R4X large. It just won't, right? So what in this case will happen, you know, Karpenter will say, okay, I need a new instance, and he looked for whatever capacity he had available that would fit the requirements. So always remember, he looks for performance and cost, and he has it spin up, you know, C5D to X large. So it's spinning up, and we can actually see kubectl get pods. We can see the status of those pods. So I have 1, 2, 3 pods that were running that actually fitted here. The other, you know, 2 pods are actually that are running on this specific node are daemon sets, the AWS node and kubeproxy that you need to deploy. And you know, Kubernetes will deploy automatically, but that needs to be deployed on those instances, on every single instance. So now it's ready, and we can see if we do get pods again, all of them are running, and I have 9 pods running, right? You know, again, it has all the 7 pods for inflate and the 2 daemon sets that is required for my pod to run. But if I go and I finally let's scale this to 0, so now I want to see how Karpenter behaves to remove. So remember, I don't have consolidation here enabled, but after 30 seconds that my nodes are empty, and you see there are 2 pods, but those 2 pods are daemon sets, and you can see here that if we do kubectl get pods -a, and we look for all the pods, for example, that are on 145, so let's just do, apologies, let's just bring this up again, and if we do -o wide, if we look for all the pods that are running, for example, the 1.9 145, I mean, they were gone. You see now they're gone, right? Like Karpenter already removed. But if you look before 1.9 145, you see here that this was kubeproxy, and 9 145, this was AWS node, which is just daemon sets that are running. But you saw how Karpenter can works. So just because I'm running out of time here, one thing I actually want to do is I want to enable consolidation. So I'm going to replace my default provisioner. So I'm going to replace my default provisioner. So what you see on my default provisioner here, now I'm telling consolidation is true. So you can see here consolidation true. And then, one second, just my computer is a little bit slow. I'm saying that I only want on demand. Now I don't want spot, and I don't want these specific instance sizes, and that's pretty much it. And remember, once you have consolidation, you need to remove the TTL seconds after empty. So I don't need that. So what I want to do now, let's inflate, let's deploy 3 replicas of my inflate application here. So remember, now I have consolidation enabled. Let's see what is the difference, right? Okay, I have said, okay, spin up 3 more replicas. Karpenter said, okay, in order to spin up 3 more replicas, now it's on demand because my provisioner said it was on demand and not using spot anymore. He found that this specific instance is the most performance and cost optimized for what I'm trying to do, is now spinning up those. So we're just gonna wait for those to spin up. Once, and you know, okay, it has a spin up. You know, remember the idea of actually having beam packing and faster scaling. Cluster scaling is going to be much slower than this. You could see that it's actually pre-pulling the image and making those cached available just when the node is up and running. So it's doing already some work before even the node is ready on Kubernetes, and you can see those details here. And off it goes. They are actually available. So if we quickly do kubectl get pods, I can see that I have 3 pods, and if you do -oy, you can see that I have 3 pods. Let's just wait a second. You can see that I have 3 pods that are scheduled 132, which is the new one. So now finally, let's deploy. Let's actually go and do the same. Let's do, okay, I want 10 replicas. So now, okay, now I want 10 replicas. Let's see what Karpenter does, right? Okay, Karpenter said, I cannot fit all the remaining 7 pods that you want me to deploy on the existing infrastructure. So now I am deploying another C2A. They are 2x large, also on demand. So let's wait and see what happens there. Let's, you know, it's taking a few minutes to actually, a minute or so to scale, to create a new instance and then deploy those containers on that new instance. But, you know, the goal I'm trying to do, you can see that you're ready before it's even ready on the Kubernetes. Karpenter is already making all the work behind the scenes. And, you know, you can see all the logs here. If you look at the logs, let's see if we get the logs here. It's just gonna 1 second here. So you can see the logs that it has deployed a new instance, and they are all available. So if you do kubectl get pods -oy-a, and we see all the pods and you see all the inflates. Now I have pods on 106, but I also have pods on 132, which is 106 and 32, the one I have deployed. So what should happen if I actually now scale my application down to 6? Remember what consolidation does, that not only remove empty nodes, but also try to make good decisions if we can do it. So I'm going to spin up to 6 replicas now. So instead of 10, I want 6 replicas. So you see that, okay, it has now, removed to 40% utilization. So let's see if Karpenter will make any decision here. It might make a decision here, or it might not. So let's just wait a few minutes. So he made a decision. He said, okay, the remaining pods that you had, the 6 replicas that you had, could actually all be filled within the 2x large. So we remove my x large instance. Before removed, of course, moved all the pods into the existing node here, because you saw like, well, you shouldn't have 2. You don't need to have 2 instances. You can only have 1 instance, keep the bigger instance, move the pods to the bigger instance, and then remove the smaller instance. So we see that. But what happens now if we go a step above? We have this 2x large. What happens if you only need now 3 replicas, right? So you only need 3 replicas. And you can see now that only 40% of the 2x large is being utilized. Karpenter should actually go and look for a cheaper instance that can fit those pods. So let's just wait. Actually, what this is going to happen here is, because, there you go. Because you can see that it's now cordon, It's waiting for a new instance, the X large, to be available, because it's much cheaper than 2x large, right? So it's waiting for a new instance to be up and running. Once that instance is up and running, it's gonna move the pods from the bigger instance to the smaller instance. And once those pods are moved and ready and running, it's gonna remove the bigger instance. So you always, long story short, Karpenter will always be looking for you for the best performance and cost optimized way. And you can create many different things, multiple provisions that will fit specific needs for your application. But hopefully I was able to demonstrate once this finished. So you see, this is ready, and it actually has removed the 2x large. And if I look at the pods running here, and we look, once just a few seconds when my page refreshes here, you see that all the inflate pods are actually now running on my specific 123 instance. So you can see 123 instances, they are up and running. So I just want to say thank you so much. Hopefully the demo was useful. Please reach me out on Twitter, on LinkedIn if you have any questions. Go ahead and test Karpenter. I would highly recommend running Karpenter on EKS. It can make your life much easier, more flexible, and more cost optimized. So hope you had fun. Thanks for tuning in, and have a great rest of your conference. Bye bye, everyone.